Okay, so this video is going to cover in your textbook pages 214, looking at the reactions of amines through to the videos on their basic nature, which brings us through to the end of or halfway down page 216, about halfway down page 216. So please make sure you've done the exercises, okay, and the reading on those pages. So we need to be able to talk about the basic strength of amines, okay, so in other words how they behave as bases and how does that basic strength differ between primary, secondary and tertiary amines. So if we think about ammonia, guys, okay, something that we did right back at GCSE, ammonia behaves as a base because it can accept a pair or it can accept a proton to form an ammonium ion, and it does it via this lone pair of electrons in the nitrogen. Well, remember, amines are exactly the same. Okay, they have lone pairs of electrons on the nitrogen. Okay, and because of that, they can behave as proton acceptors, and that's your definition for a base, your Bronsted-Lowry Base. Okay, and they do it via this dative or coordinate bond. So if we look at here, we have a typical amine with 3 R groups on it, whether it be 2 hydrogens on an alkyl chain or 3 hydrogens, doesn't matter. We have the lone pair on the nitrogen accepting a proton, and we get our dative bond here, and we have accepted the proton, and that shows that these things have got basic character. Now, we need to be able to discuss why some of them are stronger bases than others and why some of them are weaker bases than others. And it's all really to do with the electron density around that nitrogen, this nitrogen that we spoke about here, that is able to accept that lone pair, it has that lone pair of electrons and accepts the proton. Okay, so if you were to be able to increase the density of the electrons around that nitrogen, you're going to make it more attractive to this hydrogen ion, and you're going to make it a stronger base. On the flip side of that, if you reduce the availability or the density of that lone pair of electrons in the nitrogen, you're going to make it a weaker base because it's not going to attract that hydrogen ion to the same extent. Okay, well, alkyl groups have the ability to repel electrons away from themselves. This is what's called the inductive effect, and that increases the electron density around the nitrogen. That makes anything which has got alkyl groups around it in terms of an amine to be a stronger base. Aryl groups being benzene groups, so C6H5 type groups, take electrons away towards themselves. They attract electrons towards themselves. This is called the delocalization effect, and that decreases the electron density around the nitrogen, makes it a weaker base than ammonia. So if I was to compare 3 amines here, we have here an aliphatic with an alkyl group, we have an aromatic with an aryl group. Here what's happening is the lone pair of electrons, so let me just tidy this up a little bit. Okay, so on this one the lone pair of electrons are being attracted by the aryl group, okay, because of this delocalization effect. That means that they are less available. If I have a hydrogen ion trying to get them, they are less available for the hydrogen ion. Whereas my alkyl group allows electrons to drift away from it, meaning that the electron pair, the electron density, the negative density around this nitrogen is significantly enhanced, meaning that it can attract the hydrogen ion much more strongly. So my alkyl group down here leads to a much stronger base. Ammonia is placed in the middle because ammonia has neither alkyl groups nor aryl groups. So it has neither the inductive effect nor does it have the delocalization effect. So look at this in a little bit more detail just to get the picture across to you in the next video, or sorry, the next slide. So if I take a primary aliphatic, if you look at it here, what you can see is we're showing with the blue arrow the movement of the electrons, and we can see this much increased delta negative around the nitrogen, and if I have a hydrogen ion in the proximity, it's going to be significantly attracted towards it. That makes it a relatively strong base. If I was to take a primary aromatic or an aryl group here, you can see the lone pair on the nitrogen in the green. The blue is the nitrogen. That's the lone pair in the green. And what happens is that that lone pair gets pulled into the delocalized pi bonding system. So if I have a hydrogen ion now, that lone pair is in the delocalized pi bonding system, and it cannot attract or form a data bond with the hydrogen ion anymore. Okay, now you don't need to go into a huge amount of detail on this, okay, but that's the reasons for it. Hopefully you can understand it. So have a look at your question 5.9k then. Okay. Okay. Now, we will look actually just at the reactions of these bases, these things as bases, sorry. So they form weakly alkaline solutions in water. How do they do that? Well, what they do is they take a proton from the water. So if I was to sort of break water down there, takes a proton from the water. What does that leave behind? It leaves back a hydroxide ion, and that means that it is basic and has a pH above 7. Reactions with acids, you'll be asked, and you have done in the last few slides there, to write equations for the reaction of these with acids. So it's no different, guys, than if you think back even to GCSE. Ammonia plus HCl gives me ammonium chloride. Same principle here, except this time we have an R group. So we might end up, if the R group was a 2 carbon, ethyl ammonium chloride. Okay. How do we release this, the amine from the salt? So we have got our salt. How would we go back to the original amine? Share that. Okay. So go back to the original amine, which would be RNH2. Well, we've got to take a proton off this, and to do that we add our hydroxide ions, which accept protons and give you water, and that gives you the RNH2. That gives you the free base, just like we talked about earlier, where we talk about liberating the free base from the salt. Okay, I'll just clear that off so you can see the equation. Okay, now what you do need to be careful of, if they ask you, let's say for example, a question of an amine reacting with sulfuric acid, okay, and that gives me RNH3+, just the same as earlier, but we need 2 of them, because remember our sulfate ion is a 2-, so we've got to go back over here and balance that out. As so, remember there's no, when you react an amine and an acid, there's no water produced. Okay, same as when you did ammonia with an acid. Okay, so there's a question for you there. Question 2, I think that's from, if I can just find it here, exercise, I think it's 5.9J in your textbook. Okay, so based on your understanding of the previous 3 slides, complete these questions. So we've got to rank these 3 in order of increasing basicity. Okay, so pause the video, do it, and then come back. Alright, so there's an aryl one. Okay, so that's going to be the weakest, because it has got the delocalization effect. Okay, this is an aliphatic amine. That is going to be the strongest of the bases in there, because it has got the inductive effect. And finally we have ammonia, which has neither of those effects and is in the middle. The next one then, again, pause the video, read the question, have a go at it, and then come back. Okay, so here we've got a primary versus a secondary amine, versus a tertiary amine versus a secondary amine. So if you think about primaries, they only have one alkyl group. Secondaries have got, remember N, they've got two alkyl groups. Okay, so this one here has two alkyl groups, the secondary one. And then finally the tertiary one, this one, has got three alkyl groups. So the strongest base is, I'm running out of space here, the strongest base is the tertiary because it has inductive effect coming from there, there and there. So you have a really delta negative, sorry that should be delta negative ion, not ion, a really delta negative nitrogen. Okay, so here, delta negative. Here you only have two alkyl groups giving you, again, delta negative, but not as delta negative, so it won't attract the hydrogen ion to the same extent. And then here we only have one alkyl group, so again we get delta negative, the electrons drift away, but it's less delta negative than the other two, so it doesn't attract the hydrogen ion to the same extent. Okay, so hopefully you get the idea there behind that, guys. So you can see the question on the board. Okay, so comparing the solubility and the melting point of these amines and their salts that are made in the reactions with acids. So maybe you could stop the video and have a think about this one. So we have relative solubility of these two. Okay, well the salt will have a greater solubility. Okay, so this one will have a greater solubility because it's ionic. And ionic interactions have very strong interactions with water. The amine, yes, it will form hydrogen bonds with water, but hydrogen bonds don't promote solubility or allow solubility as greatly as ionic interactions. So a lot of people go for the amine on the right because they know it's got hydrogen bonds, forgetting that ionic interactions are even stronger attractions with water. Okay, the next one then. Maybe pause the video, have a think about it, and then come back. So again, the highest melting point is the salt, and that's simply because it's ionic, and ionic bonds are much stronger than the van der Waals and the hydrogen bonds that this amine here has. Okay, so same sort of explanation, but for different reasons. And that's a typical salt of an amine there that you have at room temperature. It's a white crystal, a white salt.